So in this unit, we'll talk about definition. Definition is important for a variety of reasons. One reason is this: if you fail to be clear about the meanings of the terms you use, then you can end up in a situation where you and someone else agree about all the basic facts, but you fail to realize that you agree about the basic facts because you're using some term differently. So you think you disagree where in fact you agree. And of course it can happen in the other direction where you think you agree but you don't actually, begin because you're using terms differently. It's also the case that even you yourself can end up using terms differently in ways that lead you to think badly. So suppose I make the following argument. P implies Q, therefore Q. Well, provided that P means the same thing in both cases, this argument is valid. But what if I mean one thing by P here and a different thing by P there? Then this argument's no longer valid, and if I fail to see the shift in meaning, I'll end up making a fallacious inference because I'll think it's valid when it isn't. So there's a variety of reasons why definition is important. These will come across as we sort of proceed. Today we're going to talk a little bit about what an ideal definition is. And ideal might be sort of an ideal that's often unattainable. Nonetheless, it's an ideal that's worth understanding and working towards. And we're going to talk about definition for predicates, for property terms, that is terms that refer to things like tables and chairs and trees and siblinghood and sisterhood and lunchboxness and so on and so forth, rather than terms that refer to individuals like Barack Obama, or I could give a name to the door of my office and call it John. And, then it wouldn't be referring to a kind of thing, the word John, it would be referring to a particular individual. So we're going to talk about definitions for predicates. So an ideal definition for a predicate provides necessary and sufficient conditions for its application. As in where F is an arbitrary predicate and X is an individual to which the predicate may or may not apply, X is an F if and only if, blah, blah, blah. So let's think about this real quick. If I say X is an F if some condition is satisfied, so I'll just say X is an F if X is a G. That means this individual has the property F, or the predicate F applies to it, if the predicate G applies to it. Then I'm identifying a sufficient condition for being an F. And in particular, I'm saying G is sufficient for being an F. If I was going to represent this with the arrow, I would say if you're G, then you're F. So this is a sufficient condition. X is an F if this condition is satisfied. It means that satisfying this condition is enough to make you an F. So if you're a G, then you're an F. Now in contrast, I might say X is an F only if X is an H, let's say. And in that case, I'm going to just put in that case, H is a necessary condition for being an F. Okay, and you'd represent that like this. You'd say, well, if you're an F, then you must be an H. So that's to say H is a necessary condition for being an F. So let's just look at an example. Suppose I say, let's do a necessary condition first. Being a sibling is necessary for being a sister. That's true, and the way I'd represent that is I'd say if you're a sister, then you're a sibling. So that says being a sibling is necessary for being a sister. Suppose up here I say being a sibling and female is sufficient for being a sister. Then I'd represent that like this. If you're a sibling and female, then a sister. Okay? Now, notice here that being a sibling all by itself is a necessary condition for being a sister. And you might think being female all by itself is also a necessary condition for being a sister. So those conditions are individually necessary. Each by itself is necessary. But being a sibling by itself is not sufficient for being a sister, because you could be a sibling because you're a brother. So these are only jointly sufficient. That is, only when you put them together do you get a sufficient condition. So one way to think about this is, if I say down here, being a sister is, being a sibling is necessary for being a sister and being a female is necessary for being a sister, I have two necessary conditions. But up here, when I say being a sibling and female is sufficient for being a sister, I only have one sufficient condition, because it's the conjunction of these. It's them together that makes a sufficient condition, whereas individually they're necessary. Okay. So that's the explanation of how we can break the definition into two parts. The necessary conditions, X is an F only if, states the necessary conditions. So for example, X is a sister only if X is female. X is a sister only if X is a sibling. And then we have X is a sister, these conditions are individually necessary. Then we have a sufficient condition, X is an F if, so if this condition is satisfied, then you're an F. So example, X is a sister if X is both female and sibling. So the conditions are jointly sufficient. Together they make one sufficient condition. Okay. And then in class, I'm just sort of reviewing the exercise now, because this is, there wasn't really lecture in class, there was just the exercise and some back and forth. So in class, people had to identify some necessary conditions for being an athlete, and then come up with a sufficient condition. So you might say, X is an athlete only if X is fast. You might think being fast is a necessary condition for being an athlete. And you might say X is an athlete only if X is heavy. You might think being heavy is a necessary condition for being an athlete, because you have in mind sumo wrestlers and football players, heavyweight boxers, and so on. And then you come down here and you might say X is an athlete if X plays a sport. Because you might think that if you play a sport, that automatically makes you an athlete. Now, one thing to notice is this. Your definition is coherent. That is, it makes sense. It's internally consistent. Only if your sufficient condition implies all of your necessary conditions. So, if your definition is coherent, so if your definition is coherent, meaning it doesn't contradict itself, then your sufficient condition implies your necessary conditions. Why is that? Well, imagine that that doesn't hold. Imagine you have a sufficient condition that doesn't imply some necessary condition. So let's suppose that playing a sport doesn't imply being heavy. And let's take a particular person who plays a sport but isn't heavy. Like maybe, I don't know, let's say Steph Curry, the basketball player in the NBA. Let's say he doesn't count as heavy, but he does play a sport. So since he plays a sport, he meets our sufficient condition. So then we would have to say Steph Curry is an athlete. But since he isn't heavy, he doesn't meet a necessary condition. So we'd have to say Steph Curry isn't an athlete. So then we'd have to say, according to our definition, he both is and isn't an athlete. Well, that's self-contradictory, which means our definition, assuming our predicate is actually coherent, our definition is wrong. So if the easiest way to ensure, so again, your sufficient condition must imply each of your necessary conditions if your definition is to be coherent. The easiest way to make sure that happens is just to make your sufficient condition the conjunction of all your necessary conditions. So suppose we said these are our necessary conditions, then our sufficient condition would be fast and heavy. And now anybody who's fast and heavy counts as an athlete, because if they're fast and heavy, then they're an athlete, and they count as an athlete, a given individual counts as an athlete only if that individual is fast and heavy. So you have a coherent definition. Okay. Of course, that definition is implausible, if only because Steph Curry is an athlete and he doesn't meet those sufficient conditions, so presumably we need a different condition. Now, in class, what we saw is it's really hard to come up with even necessary conditions, because anything you put is going to lead to trouble. Obviously, if I say X is an athlete only if X is fast, you can come up with a counterexample, which is a case of somebody who isn't fast, but is an athlete. Like maybe an offensive lineman in football, you'd want to say, isn't fast, but is an athlete. Of course, there are fast offensive linemen, but there are some who presumably aren't very fast. You might want to say great bowler. There could be a great bowler who's an athlete, but isn't fast. What about plays a sport? Well, this is going to put a lot of weight on what counts as a sport. So does rock climbing count as a sport even if you don't participate in any formal events? If it doesn't, then we have to say Alex Honnold isn't an athlete, the guy who free soloed El Capitan, because he doesn't play a sport. But if rock climbing does count as a sport, even when you're just going out there and doing it on your own, then it's pretty hard to see what doesn't count as a sport. So one thing I want you to be aware of is sometimes when you define one term, you're going to have your definition rest on another term, and that term also needs to be defined in a clear and coherent way. Okay. So what you're supposed to do for this exercise, and I won't say much more about it, is come up with some necessary conditions, come up with a sufficient condition, and then in class you would trade with someone, but you can just do it on your own if you weren't in class. You come down here and you come up with counterexamples. A counterexample to a necessary condition is a case of somebody who the predicate applies to, but doesn't meet that necessary condition. So suppose we said that the necessary condition for being an athlete is being tall, okay? And then we come down here, when we come up with a counterexample to that necessary condition, we'd say this: Muggsy Bogues is an athlete. He's a guy who played point guard in the NBA, even though he was only 5'3", but isn't tall. So it's someone who the predicate does apply to, so they are an athlete, but the necessary condition isn't satisfied, so they aren't tall. Now suppose we had as a sufficient condition playing a sport. Then what we'd do is we'd come down here and we'd find someone. Our counterexample would be a case of someone who plays a sport but isn't an athlete. So the predicate doesn't apply, but they do meet the condition. So who's a case of someone who plays a sport but isn't an athlete? Well, maybe you would say, I don't know, not to pick on offensive linemen, but of some offensive linemen. I don't actually know the names of any offensive linemen in football, but let's say some offensive lineman isn't an athlete, because you'd say that person's just big, they're not athletic. But they do play a sport. So I don't care if this is a good counterexample. What I want you to see is that a counterexample to a necessary condition is a case where the predicate does apply, but the necessary condition doesn't. A counterexample to a sufficient condition is a case where the predicate doesn't apply, but the sufficient condition does apply. Okay? And then after you come up with those counterexamples, you're supposed to either adjust your definition so that those counterexamples no longer apply, or you're supposed to explain why the counterexample isn't really a counterexample, why the objection is misguided. So you might say, okay, I'm going to say is either tall or super fast to take care of this, because Muggsy Bogues is super fast, so this objection no longer applies. And to take care, or you might say, I'm just going to say that Muggsy Bogues isn't an athlete because he isn't tall. Down here you might say, well, offensive linemen are athletes. Or you might say, okay, playing a sport isn't enough. You have to play a sport and be fast, or something like that. Okay? And you're supposed to just go through that iteration to sort of learn how hard it is to come up with necessary and sufficient conditions, but also to work at getting better at coming up with necessary and sufficient conditions. Okay, we'll stop the video there.